Good afternoon, everyone. Today I'm going to present the Failure-Oblivious CHERI, that is how to bring resilience to CHERI. So let's go through some background information for it. So memory safety has been one of the persistent, long-lasting safety issues in software systems. So one of them would be like the spatial memory safety, just like in non-secure a program trying to access some memory that is not allowed it to access. And then another one would be like the temporal memory safety, that is a program trying to access something that is already revoked, that is invalid then. These two consist of the major memory safety issues. Like for that case, we are trying really hard, try to solve these two problems and also many other problems, but these two are still the top two issues that we try to solve. And CHERI, as a promising software hardware approach, and try to each mitigate 100% of the spatial memory errors and to some degree temporal safety errors as well. Yes, but it also brings some new challenge to it. Like imagine you are driving a car, you have a multimedia service, you can listen to music, you can know your location, GPS, some navigation for it, and you may also able to check your speed of your car and many other details of your car as well. And suddenly, I don't know why, it have some memory out of bound access and then crash your car. Your car, the microcontroller may need to be restarted, and then your brake system may stop working. It will be really serious issues, right? You don't want your car cannot stop or cannot be controlled. So the problem will be like currently CHERI adopt a fail-stop semantic. That is, when a program have some invalid memory access, it just try to stop execution without trying to afford some recovery for it. So that is one thing is denying of service in some threat model is a kind of very serious security issue. So how do we bring availability like software which requires high availability, or how do we build some secure yet fault-tolerant software on top of CHERI in this case? So that is today's topic that I'm trying to talk about. So I guess everyone knows about CHERI, so let me skip this slide. Okay. So there are two primary approaches to the aforementioned problems. So the first one would be the failure-oblivious computing takes a pragmatic approach, that is, it allows the normal program with operations that is inbound memory access to continue to proceed normally, but for out-of-bound nodes, the system will try to suppress it, try to return some sensible values like manufactured values or default values 0 to it, so you can simply load it without crashing. And similarly for out-of-bound stores, you can simply suppress the store without crashing the program because it's still okay, simulating a well-defined behavior as it. And the boundless memory blocks takes a further step to it, so you try to redirect those invalid memory access to some kind of cache to it, so you can temporarily save it to redirect those unsafe memory operations to access our safe region to it, and then later you can load it back from there. And it tries for uninitialized memory, it tries to return some manufactured value as well, try to simulate a well-behaved system without crashing the server. I mean, that allows the computation to continue to go on. So that's how we try to bring the resilience to CHERI in this case. And let's talk about the approaches, and we have a few points of interest that we are interested in. There are two major axes that are we interested in, like how the exception direction is and how do we handle it. Like currently the CHERI, the hardware, will check for the capabilities, and then it have checks for capability violation, checks to the kernel, and the kernel will raise exceptions to the user space. And similarly, our mitigation approach can also be approached in using this way. Like we can decide whether to mitigate it from the user space, kernel, or in the hardware as we want. And what I want to talk about is two top-down approach and also the bottom-up approach. So we know that from programming language like C language, there is a concept like called no terminated byte strings. That's the no byte is using to terminate the strings. And programmers are always struggling to decide whether I should +1 or -1 for the size. Because it may miscalculate, like different libraries, string libraries or whatever, they have different meanings, like whether it's the buffer size or the string names or whatever, like here. And then ISO-C standard, they try to provide a bunch of interface, like the string names try to allow the user, developer, try to develop it. Okay, may I supply the maximum size to it? Yes, that tries to alleviate the problem, but still programmer can accidentally miscalculate the size. And you supply a one size here, like 95, you supply a one size, it still results in a buffer overflow, and your program still crashes on Cherry. So the key idea would be like the libraries can take the concept, obtain the metadata from the capabilities. So we can use these informations when we implement the library. So we designed a Cherry-aware libc in this case. So it's basically some pseudocode here, but it's trying to intersect the standard library C function. So this pseudocode here, we can say that, okay, you try to get the metadata, know the actual buffer size you have, and try to correct the bound if it is really wrong, and try to correct it. And that is from programming language perspective. And also we can also handle from the hardware perspective, because Cherry capability faults can also happen in many different places. Like we have problems with the instruction fetch values. Why? Because your program counter now have capabilities. So if you try to program counter jump to some region that you don't have capability to execute on, then your program crashes as well. Another one is trivial one, the low store instructions out of bound memory access, then you also have a crisis. So in this example, like you have some secret functions and you want to copy that one, try to use the function pointer, etc., try to execute it. It will crash on the Cherry because of this two-dimensional issue, and you try to mitigate it as well and implement it. So let me show some practical evaluation here. So illustrate my results. So one example here would be like a flow run in the glib library that is for the GTK implementation stuff as well, and also other things. Is the integer overflow results into a buffer overread. You can see in this code, the programmer, the developer, has tried everything, tried to secure the code. It tries to use the library, like the gdatetime, this library. If it returns a null pointer, it will print unable to decode it because it returns a null pointer by the API standard. If it's able to do it, okay, print the format, whatever. It also tries to free the memory as required, everything it is possible to do it. However, the CPE says that, okay, you will result in a buffer underread. It's the library function that triggers the error, something that you cannot control because it's a shared library or something. So this is the example, like the CPE run on Cherry, then you will have a core dump, but with our implementation, we can show the developer the result in the trace log. We know that, okay, there's a chap, okay, as some memory adjusts, some instruction running on each chap, and then finally returns unable to decode, which is the previous 9.6, the unable to decode. It means that the program somehow continues to run because returning C node is like returning a null pointer to it. So the well-defined programmers can continue to run the service, even though the shared library may have flaw on it. It may be good for real-time systems that you may have untrusted library, and you still want to run it, but without crashing the whole system. Yeah. And then this one, let me skip these two slides yet. So in this one, we also experiment on some high-level languages. Like in here, we are running on Lua, which is in pure cap mode, and then it is a heap use of the free bug. You can run on it, and then it's able to return some sensible value, and then Lua interpreter is have some self-checking itself, and then it is able to say, okay, I know that I have made some bug. And then if the user reports these results, the Lua developer can say, oh, okay, I know we have a bug, but fortunately still running the program without compromising the whole thing. So we still have a bunch of other CPEs, a few CPEs, and also for the pure Perl language as well. Still the same problem, but it's buffer overflow, but you're still able to mitigate it. So exists normally instead of crashing. So imagine you have some pure script you are trying to run, you don't want the whole thing to crash, but you just want to skip through the 40 executions. So the key idea from my talk is try to bring the security availability together, try to bridge the gap between the security and also the resilience, and try to strengthen CHERI's adoption in the safety critical domains like the automatives or many other things that really availability is important, like the server or many other things. So that's the end of my talk. Thank you.